Welcome to this presentation. You are watching Vlsi Design Lecture Series. Today we are going to discuss about the arithmetic building blocks and the designing of memory and array structures. Now let us focus on data paths. The components of a digital processor consist of data path, memory, control and I/O blocks that we know. The data path is the core of the processor. This is where all computations are performed. The other blocks in the processor are support units that either store the results produced by the data path or help to determine what will happen in the next cycle. A typical data path consists of interconnection of basic combinational functions such as arithmetic operations, addition, multiplication, comparison, and shift, and the logic functions are like AND, OR, and XOR. So here you can see a generic digital processor which contains all the major components like data path, memory, and control unit, and so input output units. So the data path consists of interconnection of basic combinational functions such as arithmetic and logic. So the other blocks are support units only. Here the data paths are often arranged in bit sliced organization. In some cases, such as in personal computers, processing speed is everything. In most other applications, there is a maximum amount of power that is allowed to be dissipated, or there is maximum energy available for computation while maintaining the desired throughput. The data paths are often arranged in a bit sliced organization. Instead of operating on single bit digital signals, the data in a processor are arranged in a word based fashion. Typical microprocessor data paths are 32 or 64 bits wide, while the dedicated signal processing data paths, such as those in DSL models and magnetic disk drives or compact disk players, are of arbitrary width, typically 5 to 24 bits. For instance, a 32-bit processor operates on data words that are 32 bits wide, and this is reflected in the organization of the data path. Since the same operation frequently has to be performed on each bit of the data word, the data path consists of 32-bit slices, each operating on a single bit, hence the term bit sliced. Bit slices are either identical or resemble a similar structure for all bits. The data path designer can concentrate on the design of a single slice that is repeated 32 times. Now, let us focus our concept to adder. Addition is the most commonly used arithmetic operation. It is often the speed limiting element as well. Therefore, careful optimization of the adder is of the utmost importance. This optimization can proceed either at the logic or circuit level. Typical logic level optimization try to rearrange the Boolean equations so that a faster or smaller circuit is obtained. An example of such a logical optimization is the carry look-ahead adder, and circuit optimizations on the other hand manipulate transistor sizes and the circuit topology to optimize the speed. And before considering both the optimization process, we will just take a short look on the summary of adder circuits. Now first let us look into binary adder, first we will see the full adder, which shows the truth table of full adder. Here A, B are the adder inputs and C in is the carry input. S is the sum output and C O is the carry output. The Boolean expression for S and C are written by S is equal to A exclusive B exclusive C I, where this is equal to A B bar C C I bar plus A bar B C I bar plus A bar B bar C I plus A B C I. And C dot will be equal to AB plus BCI plus ACI. It is often useful from the implementation perspective to define S and C naught as a function of the some intermediate signals, that is generate and delete propagate. The generate G is equal to 1, D is equal to 1 ensures that a carry bit will be generated or deleted. and at C naught independent of the Ci, while P is equal to 1 guarantees that the incoming carry signal will propagate to C naught. So expression for these signals can be derived from the truth table. So G is equal to A into B and D is equal to A bar into B bar and P is equal to A exclusive B. So we can rewrite the equations. C naught of G comma P is equal to G plus PCI and S of G comma P is equal to P exclusive Ci. And you can notice that G and P are the only function of A and B and are not dependent upon Ci. So in a similar way, we can also derive the expression for S of D comma P and C naught of D comma P. So an n-bit carry adder can be constructed by cascading n full adder in series and by connecting C n k minus 1 to Ci k, where k is equal to 1 to n minus 1 and the first carry in Ci 0, 0 Ci, 0 to 0. This configuration is called ripple carry adder since the carry bit ripples from one stage to another. The delay depends upon the number of delay depends upon the number of stages that must be traversed, and it's a function of the applied input signals also. For some input signals, the no rippling effect occurs at all, while for others, the carry has to ripple all the way from the least significant bit to the most significant bit. The propagation delay of such a structure is defined as the worst case delay overall possible input patterns. In the case of ripple carry adder, the worst case delay happens when a carry generated at the least significant bit positions propagates all the way to the most significant bit position. This carry is finally consumed in the last stage to produce a sum, and the delay is then proportional to the number of bits in the input words and is approximated by T adder is equal to n minus 1 into T carry plus T sum, where T carry and T sum equal the propagation delay from Ci to Co and S respectively. That you can see in this diagram. And this is the structure of the static adder. That is one way to implement the full adder circuit is to take the logical equation and translate them directly into complementary CMOS circuits. Some logic manipulations can help to reduce the transistor circuits. For example, some logic is introduced between sum and carry generations of subcircuits so that the logical implementation or the circuit implementation will become easy. So we can rewrite the carry as C naught is equal to AB plus BCI plus ACI, and sum is equal to ABCI plus C naught dash into A plus B plus CI. So the equivalence with the original equations is easily verified, and the corresponding adder designs using complementary static CMOS is shown in this figure, which requires 28 transistors. So in addition to consuming large area, this circuit is very slow due to the following reasons. The one reason is the tall PMOS transistor stacks are present in both carry and sum generation circuits. And the intrinsic load capacitance of CNET signal is large and consists of 2 diffusion and 6 gate capacitances plus the wiring capacitance. The signal propagates through 2 inverting stages in the carry generation circuit and as mentioned earlier, minimizing the carry path delay is the prime goal of the designer to speed up the processor of the adder circuits. Given the small load at the output of the carry chain, having 2 logic stages is too high a number and leads to extra delay. The sum generation requires 1 extra logic stage, but that is not that important, since a factor appears only once in the propagation delay of the ripple carry adder. Although slow, the circuit includes some smart design tricks here. Notice that you can notice that the first stage of the carry propagation generation circuit is designed with the Ci signal on the smaller PMOS stack, lowering its logical effort to 2. Also, the NMOS and PMOS transistors connected to Ci are placed as close as possible to the output of the gate. This is a direct application of circuit optimization technique, and the transistors on the critical path should be placed as close as possible to the output of the gate. For instance, in stage K of the adder, the signal AK and BK are available and stable long before CIK arrives after rippling through the previous stages. So in this way, the capacitance of the internal nodes in the transistor chain are pre-charged or discharged in once. On arrival of Ci, K, only the capacitance of the node X has to be discharged. And putting the CIK transistors closest to VDD and ground would require not only the charging of the capacitance of node X but also the internal capacitances. So the speed of the circuit can now be improved gradually by using some of the other properties. And first, the number of inverting stages in the carry path can be reduced by exploiting the inverting property. That is, inverting all inputs of the full adder will also inverts all the outputs. So this rule allows us to eliminate an inverter in the carry chain. And now let us move on to the mirror adder. An improved adder called mirror adder, which is shown in this diagram. Its operation is based on the equation which we have seen already. The carry generation circuitry is worth analyzing, and first the carry inverting gate is eliminated, and secondly the PDN and PUN networks of the gate are not dual. Instead, they form a clever implementation of the propagate, generate and delete functions when either D or G is high and C naught is set to VDD or ground respectively. So when the condition for a propagate are valid, that is P is equal to 1, the incoming carry is propagated to C naught dash. This results in a considerable reduction in both area and delay, and the analysis of the some circuitry is left, and you can observe some of the points. That is, this full adder requires only 24 transistors, and the NMOS and PMOS chains are completely symmetrical, which still yields a correct operation due to self-duality of both sum and carry function. So as a result, a maximum of 2 series transistors can be found in the carry generation circuitry. Thank you.